In the second part, I will talk about how the program runs and our baseline solution for the competition. To begin with, I will introduce the task definition. The inputs of the task include a cluttered scenes as shown in the top figure, target object poses, and object meshes. The tools that the participants can use include a Franca Panda robot with prolonged finger, an on-hand RealSense D435i camera, and a fixed Kinect DK camera. The task is to move the objects to target poses as shown in the bottom figure. Here are some examples for the challenge tasks. Then, I want to show you an example of how our baseline solution program runs and completes the task. This demo runs in the PyBullet simulator, but the real robot or Sapien simulator can be also used using the same program. In this demo, 5 loads start one by one using ROS launch command. The first node brings up the PyBullet simulator and the ROS interface. The second node starts MoveIt, which is a motion planning framework in ROS. The third node starts the perception module, and the fourth node starts the planning module. The last node triggers the task solution. We combine some of the loads into a single launch file, and you can also run 3 scripts to start the demo, which will be discussed later. As for the solution, first, the trigger node forwards the target object names and poses. Then the planning node asks perception node for object 60 poses and grasping poses. The perception module moves the robot and captures images from several different perspectives. Then the perception module generates the object 60 poses and grasp poses. After obtaining the perception result, the planning module plans the order and trajectory of picking and placing objects. Then I will talk about the framework of the whole program. The core of the program is ROS, which is short for Robot Operating System. The robot and all the sensors are abstracted as ROS nodes. Users can access this hardware by ROS topics or ROS services. For those who are not familiar with ROS, we also provide a Python interface so that they can also easily take part in the competition. As there are 3 major user nodes, namely trigger, planning, and perception. The trigger node forwards the target object names and poses to planning module. Then the planning module firstly calls the perception node for result, and then plans and moves the robot to complete the task. The trigger node also starts a clock. When the time runs out, the trigger node will also terminate. For the backend, we have both simulators and real robot. For real robot branch, the program will run on a real robot, and for simulation branch, the program runs on the simulator. We will provide both Sapien simulator and PyBullet simulator. Both real robot and simulators have the same interfaces, and the details are transparent to the users. So the participants can use the simulators to develop programs and easily transfer to real robot. To help participants complete the task, a baseline solution is provided. The solution are mainly composed of 2 parts, namely the perception module and the planning module. The perception module estimates the object's 60 poses and grasping poses, while the planning module conducts task planning and motion planning after obtaining the perception result. As shown in the previous demo, we move the robot to several fixed points and capture both RGB and depth images. The point cloud of the scene is reconstructed by ICP registration. For object 60 poses estimation, we provide 2 methods. The first one is a 2D correspondence-based method. First, we render images of objects from several different perspectives. Second, we find correspondences between these rendered images and camera-captured images using superglue. Last, we calculate the object poses by PNP-Ransack algorithm. The second method utilizes point cloud registration. First, we remove table points and cluster remaining points into several groups. Then, we generate several template orientations for each of the object model and try to match with each of the points group using ICP algorithm. The best matching poses are adopted. For grass pose estimation, we adopt grassblade baseline. Fed with a point cloud, grassblade baseline outputs several grass pose candidates. Then we assign each object the most confident grass pose. The task planning module retrieves goal objects and their poses from trigger load. Then it calls perception module and obtains 60 poses and grasping poses. The order of grasping and placing objects is planned using PDDL. The trajectory of robot is planned by motion planning module. The process will be executed repeatedly until all the objects are manipulated. The motion planning module calculates the 4 intermediate poses of pre-grasp, grasp, pre-place, and place from perception result and the target configuration. Then the joint space trajectory is generated using the MoveIt ROS package. Here, I will look into the baseline solution and checks how it works with a very simple thing that is moving a single object from one place to another. In this demo, we will adopt the point cloud matching method to estimate object 60 poses. First, you need to modify the perception configuration file. You should change pose method from superglue to ICP. And in order to better show the whole process, you can set the debug flag to true. Many other parameters are here. You can try to adjust them to meet your own requirements. Then we can start the demo by running 3 launch files. The first one starts both the simulator and the ROS interface. The second one starts the perception module, the planning module, and MoveIt. The last one triggers the solution pipeline. Now let's look at the source code. The trigger node reads target object names and poses from the files and sends them to ask planning module. They communicate with each other through ROS action. Then the task planning module first calls the perception module to obtain object 60 poses and grasping poses. The perception module contains 4 parts. To begin with, it moves the robot to some fixed points to scan the scene using Python manipulator interface and captures images and point clouds. The point cloud of the whole scene is reconstructed by ICP registration. The object 60 poses are estimated by either ICP-based method or superglue-based method. In this demo, we adopt ICP-based one. First, outlier and points of the desktop are removed. Then, several template orientations are sampled uniformly. Next, we cluster the point cloud into several groups and try to match each of the object model of each template orientation with each of the point cloud cluster using ICP. Each matching gets a score and the best matching poses are adopted. For grasp poses generation, grassblade baseline method is used, and at last we assign each object a most confident grasp pose. Then it goes back to the task planning module. The action sequence is planned using PDDL. Then the sequence is executed by motion planning, which is based on MoveIt.